Hello students, welcome to the final edition of Chapter 10, Light Reflection and Refraction. If you are watching a physics video for the first time, you can click on the link given in the description to watch the previous topics. In this video, we will be discussing the image formation by spherical lenses, the sign convention used in spherical lenses, and the lens formula. A lens is a transparent material bound by two surfaces, of which one or both surfaces are spherical. The spherical lens bulging outwards is called a convex lens. The spherical lens curved inwards is called a concave lens. Before studying about the image formation by spherical lenses, let us learn about spherical lenses first. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2, or simply 2f1 and 2f2. An imaginary straight line passing through the two centers of curvature of a lens is called its principal axis. The center of the spherical lens is called optical center, which can also be represented as O of the lens. The spherical lenses are bifocal lenses. Hence, for a spherical lens, there will be two principal foci, f1 and f2. Image formation by spherical lenses. Let us first understand how a ray of light goes under refraction when passing through a lens. Here, a ray of light parallel to the principal axis incidents on the surface of a convex lens, making an angle I with the curved surface. This ray of light now bends towards the normal and travels in a straight path towards the principal axis till it reaches the other side of the lens. Now, on the other side, light again emerges out in the air medium, shifting more towards the principal axis. In the case of concave lens, the ray of light gets diverted away from the principal axis due to the geometrical shape of the lens. Image formation by convex lens. We will be studying the image formation by a convex lens in the same way as we had learned in the case of concave mirrors. Let us start by keeping the object at infinite distance. The rays of light coming from infinity converges toward the principal axis and meets at f2, forming a highly diminished but real and inverted image. You can see the same in this animation. When the object is kept beyond to 2f1, the image is obtained between f2 and 2f2. The size of the image increases by a fraction, but it is still very small, real and inverted. Watch the animation carefully. When the object is kept at 2f1, the image is formed at 2f2, and it is exactly same as the size of the object, and still real and inverted. Here is the animation for that. Now, if we bring the object closer to the lens, that is when we keep the object between 2f1 and f1. We will see the image to be forming beyond 2f2. The image will be enlarged, real and inverted. You can see the same in this animation. When the object is kept at f1, the rays of light after converging remain parallel to each other and form the image at infinity. The image is highly enlarged, real and inverted. Let's have a look at another animation. The object is then brought between f1 and the optical center of the lens, which results into forming a highly enlarged, virtual and erect image at a point on the same side of the object. Please have a look at this animation carefully. Image formation through concave lens. A concave lens, just like a convex mirror, always forms a diminished, virtual and erect image. Let us see the couple of examples of image formation by concave lens. In the case of concave lens, when the object is kept at infinity, the virtually erect and highly diminished image is formed at f1 on the same side of the object. You can understand this by this simple animation. When the object is kept anywhere between infinity and the optical center O, the image is formed between focus f1 and optical center O. It is diminished, virtual and erect. Sign convention. For lenses, we follow the same set of sign conventions that we studied for mirrors. We apply the rules for signs of distances, except that all the measurements are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. We must take care for applying the signs of u, v, f, object height h and image height h dash. Lens formula. The lens formula gives the relationship between object distance u, image distance v, and the focal length f. The lens formula is expressed as 1 by f is equal to 1 by v minus 1 by u. This formula is, in general, valid for both types of lenses. Magnification. For a lens, magnification is the ratio of the image's height to the object's height. It is also related to the object distance u and image distance v, and it is given by m is equal to v upon u. Power of a lens. For a typical spherical lens, the degree of convergence or divergence of rays of light is achieved by its measurement in terms of power. Power of a lens is the reciprocal of its focal length. It is measured in terms of m to the power of minus 1 or diota. If you like the video, please hit the like button and subscribe to our channel for more videos.